Perfect. All right, great. Hello and welcome everybody to the Sentinel Innovation and Methods Seminar Series. My name is Rishi Desai. I'm an Associate Professor of Medicine at Harvard Medical School and an epidemiologist in the Division of Pharmacoepi at Brigham, and I will be moderating today's session. The US FDA Sentinel system helps address questions related to safety and effectiveness of marketed medical products. Innovation Center focuses on developing new methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities. And the Operations Center focuses on supporting the FDA in the use of the Common Data Model and associated module program to gather evidence to support regulatory decision-making. We launched this webinar series to engage with experts and innovators in key areas related to Innovation Center's Master Plan and Operations Center's methods work. With that, I'm really pleased to introduce today's speaker, Dr. Pam Shaw. Dr. Shaw is a senior investigator in the Biostatistic Division at Kaiser Permanente in Washington Health Research Institute, with expertise in measurement error, design, and analysis of complex epidemiologic studies, clinical trials, and survival analysis. Dr. Shaw's current research focuses on methods and two-phase research designs to allow correction for covariate and outcome measurement error. Applications to studies reliant on electronic health records and large observational cohorts. She is the co-director of the Data Analytics Core for the Adult Changes in Thought, ACT, a long-running study of aging, and has continued collaboration with a variety of epidemiologic and clinical studies with focus on chronic and infectious diseases. She's an affiliate professor in the Department of Biostatistics at the University of Washington, and she has published many papers related to her works. The title of the presentation for today is Assessing Treatment Effects in Observational Data with Missing Confounders. This is a comparative study of practical, doubly robust and traditional missing data methods. So this is something we are keenly interested in as the Sentinel program. It tries to include more and more electronic health record-based data. So without further ado, I will hand it over to Pam. But before we get started, I would like to mention that all your lines are muted. So if you have a question, please type it into the Zoom Q&A feature, and we'll answer all the questions at the end. This session is also being recorded and will be made available to the public on Sentinel webpage, which is sentinelinitiative.org. So without further ado, I will hand it over to Dr. Shaw and thank her for joining us. Take it away.
Thank you, Rishi, and thank you very much for this invitation to share this work with everyone today. I'm very excited to take advantage of this opportunity. So with that, just organize my cursor here. I'm going to get started. So I do want to start with a disclaimer that the views expressed here in this presentation represent those of myself, the presenter, and do not necessarily represent the official views of the US FDA. This work was supported by the Sentinel network and within the FDA, and we have our task orders there. But this work actually had the input of a lot of people. I was very fortunate to be able to be collaborating with a number of experts in the field who throughout the work offered much great input. And so I just want to acknowledge the scientists here at Kaiser Permanente Washington Health Research Institute, folks within the FDA that have been contributors in Sentinel, and certainly to my project at Sentinel Operations Center, Brigham and Women's Hospital, Harvard, where Rishi is, and you'll see TL Revolution, Berkeley, University of Auckland, Vanderbilt, and University of Washington. So it was a lot of interesting interdisciplinary discussions that fed into this work. So I'll give you a bit more of an introduction of the motivation of this work, and then I'll describe the methods, which I expect are new to many of those on the call. And then a big part of this work is numerically evaluating these methods to help elucidate their properties for the setting of interest. And we'll be thinking about synthetic data. What I mean by that is data that was completely generated with statistical models. And then another type of numerical study, which uses Plasmode simulation or Plasmode data, which is sampling from real data to create more realistic covariate distributions. And then we'll briefly provide a link to where you'll be able to find software and vignettes so that you could apply these methods. And there'll also be a summary of some of the key findings. So the Sentinel, and I do have a website later on in these slides where you can read about this really interesting project within the FDA that's helping build methods to answer important real-world questions about treatments, efficacy, and safety. We were really particularly focused, so the Sentinel Causal Inference 4 is a project within this large network, and we were really focused on evaluating and comparing methods to arrest missing data, particularly in the setting with high levels of missing data in the confounders. So that's, perhaps a unique setting compared to what people usually study within the big field of missing data. We wanted to study estimators for so-called two-phase data, which I'll introduce more carefully in a few slides. And these include survey calibration methods and two-stage targeted maximum likelihood estimation, or TMLE, is a particular method I'll be referring to a lot today. So these two methods I expect are new for many of you. Certainly for myself, even working with TMLE, was gaining a lot of experience on this project in particular. And we wanted to compare these methods to ones you may have seen that are more commonly applied, particularly in the setting of missing data, and that includes inverse probability weighting, multiple imputation, and some other approaches which we'll call so-called naive, in the sense that they don't have a lot of statistical robustness and have usually undesirable properties, things like complete case data or just dropping variables with missing. So we'll think about those common methods and see how they compare to the methods of interest. And we were really focused on practical implementations. So we were using software in R, packages in R that we could then be easily adopted by folks within Sentinel or more broadly. And we did build on learnings of a previous project, which I'll discuss briefly within the Sentinel framework, this Causal Inference 3 project. So that project had the same setting of interest, which was thinking about approaches to handle partially observed confounder data from electronic health records in non-randomized studies of medication outcomes. So they're really building toolkits to help diagnose the kind of missing data you had and did simulation studies to provide guidance into what might be the best methods to apply for the setting of interest, partially observed confounder data. So they too were thinking about some of the standard methods, inverse probability weighting, complete case, and they were really focused on multiple imputation as the method that they expected and did see would have the best properties to have reduced bias, increased efficiency over some of the other methods. And they also wanted to think about varying mechanisms. So missing data can be missing for different reasons, completely at random, missing at random, which means you had the variables to predict what led to the missingness, or missing not at random, where you didn't observe the information that would allow you to predict why things were missing. And in that project, they did find that mice, which is this multiple imputation using chained equations procedure, which is in SAS, it's in R. They particularly use the package in R, just using the default settings essentially, did really well. And so did this random forest implementation within R and mice. And in fact, the random forest, I think, typically had the best overall performance. So we wanted to build on that, and we wanted to fill in some gaps. In particular, we wanted to think of higher levels of missingness. And we also wanted to think about these other approaches that people are less familiar with. So we wanted to, again, look at these top performers, mice, multiple imputation with random forest, and compare them directly to these two new methods, survey calibration and this TMLE-based, which is kind of a machine learning super learner type approach. Our first hypothesis was there were going to be some settings where there would be advantages to survey calibration, because it doesn't need to impose as much modeling assumptions on imputing the outcome, modeling the outcome in the people that you don't have complete data on. We also thought there would be advantages to using the TMLE, super learner, machine learning approaches because of its flexibility in modeling and actually some special features in how it estimates. It puts extra precision or attempts to reduce bias in the parameter of interest rather than kind of spreading it across nuisance parameters. And so it has very desirable properties. And we thought, obviously, having some flexibility and more non-parametric approach in complex settings could offer advantages. Like I said, we really were interested in pushing these methods to higher levels of missingness, which can happen in our setting. And we wanted to make sure that these methods were as practical to implement as we were hoping they were. So we're going to, what the work I'm presenting today is we performed a numerical simulation study to evaluate these methods under various scenarios that included high percentages of missingness in the confounders only. And we used synthetic data to really manipulate data to create some pathological scenarios And then we used the Plasmode simulation. What I referred to is we're going to use realistic covariate distributions by resampling real data and then building models on top of that. And our ultimate aim is going to be able to have a white paper and manuscripts that will be able to provide guidance on the choice of the analytic approach and some of the settings that led to particular methods doing the best. So we really want to disseminate knowledge about these methods, and we'll be providing vignettes, sort of online descriptions of how to use packages in R and samples of code and software to allow easy adaptation of these methods, adoption of these methods by members of regulators within Sentinel, researchers in the broad research community. So, why are we interested in large amounts of missing data? So when we're in the pharmacoepi setting, as many of you probably have experienced yourself, when you're evaluating treatments for safety and rare outcomes, it's often necessary to merge multiple large databases. That helps improve statistical power. That creates a more generalizable cohort with a broader set of individuals. But what can happen is that there'll be some of those databases will have more data than others. So in Sentinel, where you might have data from both administrative claims databases and electronic health records, when those are being combined, there's going to be certain kinds of clinical data that will only be in the EHR and they won't be in the administrative data. So, so that really was behind the broad interest in settings where there'd be large missing data in confounders. More generally, there are many settings in observational, even randomized cohorts, where certain covariates may only be obtained on a subset because they're invasive, spinal tap or biopsy, or they're expensive novel assays. And so this can occur for a variety of reasons. The setting what we use to do our Plasmode simulation or real-world data setting came from a data set within the KP, Kaiser Permanente, Washington health system, which is an integrated healthcare system in the Pacific Northwest, provides care and health insurance to over 700,000 members. Its data includes both claims and EHR. So we were interested in a cohort of individuals who were initiating antidepressant medication or psychotherapy over a particular period of time, roughly 10 years. And in particular, to be initiators, you couldn't have any antidepressant fills or psychotherapy in the prior year. So we had this data set of these initiators, adults 13 and over 112,000 people. But there were about 50,000 people who had complete data on all of our confounders, which included the main one, prone to missingness, which came from this patient health questionnaire, which I'll refer to as the PHQ-9. That questionnaire included important confounders regarding the severity of depression and history of prior self-harm, which may be used in treatment decisions. And so that these are key confounders in an evaluation where you might be comparing antidepressant medication versus psychotherapy. For instance, someone's depression may be so severe they're not willing to do psychotherapy alone. And so that introduces that confounding where the severity is determining the disease, the treatment itself, and possibly also the outcome of interest. So our composite outcome of interest was going to be, our outcomes of interest was a composite of self-harm or psychiatric hospitalization within 5 years of treatment. And we also thought about a self-harm only outcome. So we'll get back to those Plasmode simulations in a bit. So what I'll do next is talk a bit about our methods and then introduce our simulation studies and results. So the way we're thinking about these methods, we can think about missing data as, in fact, a type of two-phase design where you have certain variables observed on everyone. For us, that's going to be the treatment, which we'll think of as a binary treatment. We would have a bunch of confounders that would be available on everyone, and we would have that binary outcome of interest. And then, like in our ADI or antidepressant initiator cohort, there would be certain variables that would be only available in a subset. For us, those are additional confounders that would be available on some individuals. Sometimes there's very few equations. Occasionally, I might be referring to those as W as a different kind of confounder compared to the Z's, which are observed on everyone. So the two-phase study design is the idea that you have a cohort of a total of large N individuals for whom some of them with sampling probability pi I, they're getting selected into the phase 2 design where you would have all data on that subset. The missing data scenario is simply a two-phase design where you actually don't know this probability of sampling, and that will need to be estimated. So we've already mentioned several of the other types of methods that we'll have in our mind as we compare these two-phase methods. And we'll see the advantages that the two-phase methods have that some of these other methods do not have. So just to refresh your memory, we think about complete case analysis, where we would just drop individuals that were missing some information, say on key confounders. We have there's lots of problems with that. The two key ones are that when you drop individuals with data, you're losing information that can lead to inefficiency, wider confidence intervals, because you're not using all the data. Problem two is that you could be creating bias in your inference, bias in your treatment effects that you measure. And that is, a bigger problem, I think, in terms of being able to not get reliable answers to the question of interest. The confounded approach, when you have a variable that has a lot of missingness, the overwhelming temptation, I think, is to drop it. You don't have the ability to model it. But dropping confounders, it leads us into confounding bias. Now we're worried about getting an answer that also could be misleading. Inverse probability weighting is a principled approach trying to account for the individuals with partial information by weighting back to the original population to avoid that bias. So you can use all your confounders to avoid the confounder bias, and you can weight back to the population so you avoid some kind of selection bias from simply dropping individuals with partial information. The problem it doesn't solve is that it's not fully using all of the data on the people with partial information. And that's the problem that other missing data methods try to solve. Multiple imputation tries to solve that problem by actually using the data you have to impute the missing data and then go on to analyze everyone. So that's why it's typically seen as more efficient, have more precision than something like IPW that's not fully using all the data. So under the ideal circumstances where you've done your imputation correctly, you've solved all the problems. You've got efficiency, using all the data, you've avoided the selection bias and the confounding bias. But with that benefit comes a bit at a cost, in that you've had to add assumptions, particularly in how you're imputing the missing data for multiple imputation. So we wanted to think of a different way to improve over the IPW. So we're going to have principled answers that deal with the selection bias. They're going to allow us to adjust for all the confounders that we want, but that we want to improve the efficiency. We want to use all the data, but not making as many assumptions as a multiple imputation does. So we'll have some extra robustness. So we want to be more efficient, but also have a little bit more robustness. So inverse probability weighting doesn't use all the data. Our survey calibration and TMLE will be using all the data. I would just wanted to reference, and my slides are available, this outcome of the previous Sentinel project did a really great job of really demonstrating how well the multiple imputations do in terms of actually addressing some of the bias IPW can have if its missing data model is wrong, as well as the efficiency problems that IPW can have. But as I pointed out, and here's a reference from Kyung-Hee Han and others, that demonstrated that efficiency of MI comes at a cost. Like, you actually can see mathematically, and another paper by Thomas Lumley, that the efficiency you're gaining can be quantified as the robustness that you're losing in some sense, in a mathematical sense. And so I encourage the mathematicians in the audience to seek those references out. So we're going to take that information and build robustness instead of throwing it all at efficiency. And we're going to do that. The first method we're going to try to use is the survey calibration, sometimes also referred to as generalized raking. So these estimators will be generally more efficient than IPW. Whenever there's at least some linear correlation between the observed data and the unobserved data. That's very abstract, and I'll make that more precise in a few slides. And we're going to do it making fewer modeling assumptions. So the actual analysis is very similar to IPW, but there'll be one additional step in the middle. So we can think about generalized raking, which is the term I'll mainly use, also known as survey calibration, which comes from the survey literature, where you might have had missingness in response to surveys, is where this originally came up. So generalized raking, it's a complete case estimator. It's going to reweight the complete data. So your first step is to actually calculate these IPW weights, to estimate them. The second step is the new step, where these weights are going to be adjusted so-called calibrated, using the data that you have on everyone. And that's where you're going to get your efficiency gains. These calibration variables can actually be imputed using multiple imputation type tools, but they're being used as a working model. That working model can be wrong. If it's wrong, you might not gain much efficiency over the IPW, but it's not going to be introducing bias in the way we're going to be using it. And so that's the benefit there. We're going to gain efficiency without relying on the model to be true. And then the third step is going to be to simply fit a weighted outcome regression using the calibrated weights. So the first and third step are the same steps you would do for our IPW. So if you've done that, survey calibration is in your reach. Some observations, which is the ideal ranking estimator is asymptotically equivalent to the optimal augmented inverse probability weighted estimator. So that's a class of estimators that is trying to use information both about the missing data model and the outcome model in a way that adds doubly robustness, and ideally with the ideal augmentation variable, you can maximize the information from the auxiliary data from our phase 1 data. So generalized ranking is targeting the estimate that you would have had you had no missing data. And this can be readily implemented using the survey package in R, this calibration step. There's a function called calibrate. And we can we will be providing software and vignettes that show you how to do this. And so I have a link there. The site is just in its infancy. We'll be in the next several weeks adding all of our code. We've seen very recent work completing. So when we construct these ranking variables, so the idea is we're going to have an auxiliary variable that we have on everyone, and we're going to use it to adjust the IPW weights for those complete cases. Now that the choice of that, you may think you're just grabbing variables from your data like demographics or clinical information. That's not actually how it works. What you want to do, we know from a few sources, in particular, there's a citation by Norm Breslow who points out when you're estimating a regression coefficient, you want to be targeting the variable that created that regression coefficient. And each person actually has what's called like influence, like a delta beta, an influence function, their contribution to the final estimate of that regression estimate. And those are the auxiliary variables we want to create. And so there are statistical quantity that derive from the other variables in the data. And so there's actually a very practical recipe to do this. And in this one particular paper shows how we try to estimate the optimal ranking variable, which comes from trying to estimate what is our expected value of the so-called influence of this person on the target of estimation, given our observed data we have on everyone. So we wind up using a familiar tool like multiple imputation to multiply impute the missing data. And then we fit our target working models. What is our outcome model that's adjusting for the confounders and say the propensity score? And we're going to get influence functions for that final beta in that working model. And those are going to be the auxiliary variables. So we're not relying on that target model to be true, but we're going to go through familiar steps to create these variables that we're going to have on everyone and use that in what's called the calibration step. So there's a series of familiar steps where we impute missing data, we fit a target outcome model that you wanted to fit had you had complete data. We get these estimated influence functions. We maybe multiply impute it and take an average. And that is our auxiliary variable. And there's a technical bit where how the math does it. How do we get these adjusted weights? The simplest idea is there's some variable A that you have on everyone, and you want to find an adjustment to the IPW weights on the rightmost side here of that first equation, where the adjusted weighted sum of that auxiliary variable in this subset is going to equal the sum on the whole. And you want to pick these adjustments so that your weights wind up as close as possible to those original IPW weights. And the math predicts that you will shrink the variance that you would have had if you had done just plain IPW by a factor that relates to the correlation of these auxiliary variables that we're constructing and the true version of those in which you don't observe had you had complete data in the whole population. So there is a really interesting mathematics behind this, but the tool itself is fairly simple to apply. Take it from me. If I can do it, I am confident that you can do it. So that is a introduction to the calibration. The TMLE superlearner is a really interesting machine learning approach that has come up in the last 10, 15 years. which is trying to improve estimation for the parameter of interest. So it does want to target the MLE, the maximum likelihood estimator that we would usually have gotten from our regressions for the parameter of interest, but it's doing it, you're trying to reduce bias, ultimately variance for that parameter, at the expense of the nuisance parameters, all the other parameters in your model that you wouldn't be interested in. So for us, we might be interested in a risk difference for a particular treatment. That would be our parameter of interest that the machine learning would target. And it would do this by fitting multiple models to the data, what's called a superlearner, for some of the key quantities that you need to get your final estimate, say a risk difference. And it is unique, I think, one of the few really advanced machine learning methods that naturally lends itself to statistical inference, so confidence intervals and p-values, and that's why we like it. It also has really nice statistical properties in terms of when you've got your model set up correctly for the outcome of nuisance parameters, you're going to be maximally efficient, and and it has a type of double robustness property for the confounding and the outcome model. Sherry Rose and Mark Vanderlaan developed a special version of the TMLE for these two-phase designs. So it's going to allow us to do a sort of an inverse weighting solution similar to IPW, but using these advanced tools for our nuisance parameters and outcome model. So that's a very quick introduction to the TMLE, but I've got some references here. Particularly, there's a gentle introduction to TMLE that I highly recommend with Susan Gruber and Mark Vanderlaan to get started with these. But there is software in R that makes these very tractable. You just need basically to get started in terms of understanding the kinds of things you need to specify to get these models to work. Ultimately, TMLE is targeting the causal estimand. So it's trying to figure out what is the probability of a particular outcome given a treatment strategy, say a treatment, you receive this antidepressant treatment at initiation, or you're getting a psychotherapy. And you might be looking at a marginal risk difference in the probability of that event, or a risk ratio, or an odds ratio. Behind the scenes, underneath, the TMLEs are estimating that treatment effect by looking at all the confounders, those that you have complete data and not, to get at these marginal estimands. We really wanted to think about, if you had your usual analysis approach, how you like to deal with confounding, how you like to deal with modeling your outcome, whether you've got a marginal estimand or a coefficient in a logistic regression, what we might call a conditional estimand. What if you just swapped out how you were dealing with the missing data and you used this machine learning type approach? We're going to call that method the TMLE-M. And so we would use whatever our standard approach. For us, we might think for IPW or multiple mutation, we're going to do a logistic regression to estimate our treatment effect. And we're going to use adjustment in that to adjust for the variables determining the propensity of our treatment assignment. And then we would just swap out, we're not going to use missing multiple mutation. We're not going to use IPW. We're going to try these super learning approaches to model the missingness. And so we're going to, it learns across, we're going to try boosted trees and random forests and GLM. That's a little bit of an unnatural way. If you're going to, folks who are doing machine learning, they know the benefits of that. They're going to want to apply it to all aspects of your model. So how you model the treatment propensity, how you model the outcome, how you model the missingness. So we will look at that estimator. We'll be using this suite of estimation approaches within the TMLE superlearner. As it's in the machine learning, it's sort of integrating its knowledge across all these different algorithms, and we'll call that the TMLE MTO. So full modeling of this TMLE across the missingness, the treatment, and the outcome. Okay, so that was a bit of an introduction to these methods. One of the goals of this webinar is to give you some familiarity with these methods, as well as show you how well they perform. So our base case setup, and that's probably where I'll spend the most time, and just briefly talk about how the variations around the base case worked. As we thought about a cohort of 10,000 people in our synthetic data. So I'll first provide a description of our synthetic simulations, and then we'll go to our Plasmode simulations. So we'll have a cohort of 10,000 people. We're going to repeat our modeling across 2,500 data sets, and then we're going to integrate the method's performance in terms of mean bias, median bias, empirical standard error, the mean absolute deviation, root mean squared error, oracle coverage, and nominal coverage. So the root mean squared standard error, we'll be thinking about squared bias and variance of the estimator across the simulations. That's a key quantity for us. And we'll be thinking about robust versions of that rely on the MAD, which is a robust version of the standard error across the simulations, and the median of the coefficient. That's a key quantity to compare methods. And the coverage would be within each of the data sets, if we formed a confidence interval, what percentage of the time would it have contained the true estimate, which we know because we simulated the data. And we're hoping for 95% confidence intervals would capture that so-called truth 95% of the time. We're going to introduce a concept called the oracle versus the nominal coverage. Nominal coverage would use the standard error produced by the software for that method. For each confidence interval, the oracle coverage, we can actually get the true standard error, the empirical value across all of our standard deviations, so that we can just concentrate on bias and not worry about coverage problems that might have related to standard error problems, which in theory we could fix. So we're going to have 2,500 data sets. We're thinking about 40% missingness to start in the confounders and a 12% incidence in the outcome, a binary outcome. And that roughly translated to something like a number of events that was similar to some of our Plasmode scenarios. We'll be thinking about complex outcome models and missingness models, such as how the data are being truly generated for those aspects, and simple ones, because those choices, by no surprise, a complex data generating mechanism, the more complex estimation methods would do better than the simple, and vice versa. We'll think about increasing the missingness and driving down the number of events and the rarity. So we thought about all the estimators I've mentioned. The oracle and the population models are these magic benchmarks that you don't normally observe. So the oracle model is if you actually knew the true treatment effect in the population, which might not correspond to the treatment effect in a working model that you maybe posited a simple linear logistic regression model. The reason to fit both those benchmarks is, depending on your estimation technique, it may be targeting a different model. For instance, a typical missing data method is just trying to get the same answer you would have gotten had you had complete data, regardless of whether or not that model is actually the true data generating model. But some estimators, such as those using a TMLE superlearner, are trying to actually not fit a specific parametric model, the population model, but actually try to get the causal estimate for a true treatment effect. That's why we call it the oracle. So keep that in the back of your mind. And we'll look at that in pictures where maybe it'll make more sense as I just describe it. So we're thinking about the generalized ranking, this new survey calibration approach, the TMLE, and our typical multiple mutation estimators. We chose the estimators that did well in the previous work in Sentinel, which was mice in the random forest, for this setting. And we added on XGBoost, which is using another machine learning technique to impute the missing data, which is gradient boosted trees. So I mentioned already that the different types of methods are targeting different estimands. So we're going to study both marginal causal estimands and the conditional estimands. So conditional estimands would just be that coefficient in logistic regression model, conditioned on the other variables in your model. And the marginal estimands would be looking at an average treatment effect. The census and oracle estimands, I mentioned, you might be trying to target a true underlying relationship. You might be very specifically interested in coefficients in a particular model. And so the census estimand would be that benchmark if you were interested in the fitted working model answer versus some underlying truth. Common implementations, I think, of the complete case, the IPW, multiplication, generalized ranking, are generally going after that conditional estimand, the coefficient in your fitted, say, logistic regression model, and they're going for that answer you would have had you had complete data, what we call the census. And the TMLE really is going after the marginal and an oracle in terms of how it's targeting its estimation. So we're going to look at both so that we don't pick an estimand that favors a particular method. And we are going to be looking at complex and simple data generating mechanisms to see how that affects the method's performance. Just a note, in our complex Plasmode simulation, we definitely generated more complex in our simulated data, much more complex relationships than our fitted models, because we believe that's actually what usually happens. But we're using realistic distributions for the data when we do that. So this slide is a little busy, but I think I've already said the main components, which was when we do our analysis of a treatment effect, we're going to need to build our outcome model. We're going to need to build our treatment model, which is going to adjust for the confounding, the propensity to be treated. And we're going to have to build in missingness in terms of what we're going to generate, and then in an analysis model, how we'll estimate that. For our data generating mechanisms, the simple versions will use linear logistic models for that binary outcome, for the binary treatments, and the binary missingness indicator. We will create MNAR, that missing not at random, and the MAR mechanisms, and we'll create simple ones where it's just linear models so that our parametric model, our working model, will be true in those simpler methods, and a complex model where we've added interactions that perhaps mice doesn't know about and isn't in our working model for any of the methods that need to specify that working model. And in the Plasmode, the way we created complexity to try to get data as realistic as possible and yet still know the truth, so we're still using statistical models to generate the truth. We use tree-based, really complex random forest type implementations to get our outcome, missingness, and treatment models, and then complex GLMs where we were using extra interactions and discretizations of variables that were more complex than our analysis. So in summary, we had to make those model choices for our data generating mechanism, but for analysis, we're gonna be an average applied person where we have just for many of these methods, we're going to have a simple linear model, a linear working logistic model for our outcome, for our treatment, and we're just going to use confounder adjustment in that outcome model, and we're going to keep that fixed so that we can just vary the missing data method and see how that affected performance of our estimators. I think I'm going to skip this slide. It's just sort of emphasizing what I've said in words, which is these are really simple models with just a couple of confounders known on everyone. When we did the missingness, we did create a dependence on the outcome. So the slide is mostly there to remind me to tell you that, which is going to mess up complete case data royally. In our complexity, we just added what you can see, these terms, like things like kinks at the end of the linear relationship on either side and interactions with the variables prone to missingness. And that was, we thought about a null treatment effect and a non-null. I'll present results for the non-null. Okay, so that was a lot of introductions. So now we're ready to look at results. And the big reveal is the methods that are used the least do the best. And that is a bit of an oversimplification, but let's see what I mean. So in this case, let's orient ourselves to the slides. The first box plot is percent bias across the 2,500 simulations of our synthetic data. The next set of bars, the middle graph, is this root mean squared error. So the square root of the median bias squared and the MAD, that robust estimate of the standard deviation squared. So that's the bias variance trade-off. So to be lower is to have a good balance of bias and variance. And then the final is looking at the coverage of your nominal coverage, which is how often did the confidence intervals being generated by your software capture the truth. You want that around 95% because we did 95% confidence intervals. The blue line is marking where you are. And so we have these colored bars where we have the simple that would be correctly modeled by those parametric models, missingness, and a simple outcome. So simple means correctly modeled by a simple linear outcome model. And then complex is we threw in those complexities of interactions. So this is all MAR. And what we can see when we do those different combinations that, you know, my first thing I want to know, because I want valid confidence intervals, I want valid testing, is I want to see who's maintaining that 95%. I don't want it above that line because then it would be inefficient. I don't want it below that line because then you have bias. And what we can see is actually just generalized raking, both TMLE methods, and actually random forest does pretty well, although ironically in the simplest situation it had a little bit of undercoverage. But mice didn't do very well because there are two cases, and we can look at those cases. Those are the two cases where mice fails, that multiple mutation with chain equations. When you had a more complex outcome, extra variables that the imputation algorithm just didn't know about in terms of you observed those variables, but you didn't put the right functional form to mice. You didn't give it the interactions, say. So the outcome model wasn't quite imputed correctly, even though it was a super flexible algorithm and that you gave it at least the variables that were in play. So it was really exciting to see that several estimators did achieve 95% coverage, even in situations where they weren't guaranteed to do well. So that's saying there's at least some robustness to some of the assumptions. Now, survey calibration is doubly robust from the point of view of if you've got the outcome model right or the missing data right. If you've raked with ideal variables, you don't need to get both of those models right. So there is some robustness built in, but even the last scenario where both models were essentially wrong in survey calibration, perhaps through the correlation and the kind of structure wasn't too complex in terms of the complexity, we still managed to have good performance. It was at least encouraging that we kept up with the TMLE, because when we look at the middle graph, what we're seeing is mice and generalized ranking are both leveraging information. They have much smaller root mean squared error, much more efficient, lower bias overall, and better efficiency, narrower confidence intervals than IPW. And they also were more efficient than TMLE. So TMLE did great in reducing bias, but sometimes, well, and actually in all these scenarios, it still had wide confidence intervals. And you can see those, you can see that the complete case, the confounded, and even the IPW had problems with bias. And so that these methods such as generalized raking and TMLE have a double robustness property that's helping them. And perhaps the flexibility of mice is, which isn't necessarily doubly robust, but the flexibility was also helping reduce bias. So these are general trends. Mice does pretty well overall, but it does fall down when you have a much more complex outcome model that we leveraged for efficiency in the generalized raking, and but we didn't rely on correctly modeling it. So that was a nice example. And so what we looked at there was this, what I call the census, and it's the beta parameter in the logistic regression. You're trying to estimate what you would have gotten had you had complete data on everyone. The story was actually very much the same for these particular scenarios when we looked at that oracle. So sometimes that effect estimate was different because of the complexity. So the census estimate for the working model, which was linear, was different than what the complex true data generating model would have said about treatment effect. But interestingly, for that bias variance trade-off, generalized raking was still doing the best in terms of across all scenarios. The imputation models were doing quite well, actually, because if you look in these oracle estimates, the imputation and generalized raking, all the methods there to the right, which we think are the more sophisticated missing data methods, they're actually all doing pretty well for the treatment effect on the oracle scale. And that was interesting to see. And I say that because we've reduced bias, we have good coverage, and the standard errors are working well. But in some cases, the multiple mutation, particularly when the outcome was simple, eked over a little bit more efficiency over raking. But then there were other times, actually in these cases, they actually did very similarly. I think they were within 5% of each other in terms of who, given that they all seemed to reduce bias, who was the most efficient. I would say it was generalized raking, or maybe slightly edged out by random forest in this case, which did agree with the initial work of the previous group that saw that random forest could edge out mice in several scenarios. So what happens when you increase missingness? So we were really interested in kind of degenerate almost levels of missing data, like going up to 80%, because this can happen when we're merging databases, and only a subset that could be quite small have the gold standard data on all the confounders you would have wanted. So remember, we had a cohort of 10,000. Now we have 80% missingness and only an incident rate of 12%. So we have very few, maybe 100 to 200 events, on the math right. And what we can see, it was really amazing, was that these methods, when we look at the 95% coverage, that's integrating. Did we address the bias of confounding and missing data? When we hit close to 95%, the answer is yes. TMLE is doing what the theory predicts, which is does very well at addressing bias, But now we see random forest has fallen down. So it was looking like the most efficient in this with the lowest bars, just going back a slide, when we had 40% missingness. It really did have the lowest amount of root mean squared error, but now it's having trouble getting the right confidence intervals when we go to smaller data. So maybe random forest isn't a good small data method. And mice actually still did well when the outcome model was simple, but it had the usual problems when the outcome model is very complex. It wasn't performing as well as the other methods, generalized raking or the TMLE. And I'll pause to state the obvious that IPW is going to be really variable with this small amount of complete cases, now not leveraging all the data. It's suffering more, and the confounded and complete case just have the same bias that we've seen before, to the point where you can barely even see the nominal coverage because it's down at 0. When we do 80% missingness, then we drive down the incident rate. So now we're getting events that maybe in total are only about 100, and we're using these super fancy methods. We did worry, are they all going to break down? And the answer is no, they don't all break down. There is some nice tuning parameters going on, I know, within the TMLE to prevent overfitting, and you can see it's more successful at just maintaining close to 95% confidence interval, so valid inference, even though we've got a lot of complexity in that last case, very small number of his events, that it's doing quite well at getting close to the nominal coverage. Now, the reason it's failing actually has nothing to do with the bias, but in fact that the standard errors in these tiny sample sizes, maybe only 100 events or so, standard error estimates aren't performing as well. So I want to introduce the concept in just a second, which is, so the TMLEs have successfully addressed the bias, but the current software perhaps needs some improvements for small samples or refinements because the standard errors we can see are giving the TMLE problems, because theory predicts it should still do well in several of these cases when you have these simple models that it should be able to correctly model the bias. So, if you just looked at efficiency, it's like, oh, I would like to do imputation because of the multiple imputation with random forest had the least amount of variance, that squared variance plus bias. I mean, you might think if estimation is your only goal, you want the least variable estimate. That may be one perspective, but if you're worried about validity of your testing, you would worry quite a bit about random forest or some of the settings with mice, that it could be quite far compared to the other methods available to you from the 95% coverage. So you do have to start to pick an inference goal when thinking about what losses do you want to avoid. If you want to avoid inflated type 1 error, you're going to worry about any method that can't get 95% confidence intervals. And this is the one caveat that I could see is in the current implementations of TMLE, it was having a little trouble with those confidence intervals in the package, how we were using it, with that caveat. Generalized raking had the opposite problem in the sense that its standard errors were breaking down a little bit, but it was getting unstable or too wide confidence intervals. So at least you knew you'd be looking at conservative inference and not inflated type 1 errors. And we could see in this particular scenario where it was very similar to our base case, 12%, I'm sorry, not 12% incidence, but the kinds of models and missingness that remain the same. All we did was drive down the event rate. If we were to use the Oracle coverage where we cheat and go look at 2,500 simulations and get the actual standard error, we could see with perfect standard errors, the 95% confidence interval, the Oracle coverage was great for generalized raking. And TMLE specifically, when the missingness was correct, it had a little bit of trouble in that complex outcome. I'm sorry, let me make sure I get this right. The second and the fourth are the complex MAR. And the reason being that the way the software that we're using is built for this two-phase TMLE, how we've implemented this algorithm, is it's doubly robust for estimating the confounding and the outcome model. So if you're getting those nuisance parameters, one of those modeled correctly, you should see that 95% confidence interval, that the bias, it is eliminating bias, but it is relying on a type of IPW weighting for the missingness. So even though it flexibly modeled it, there was still an issue with not having that full robustness against the missing models. I probably said that slightly imprecisely, but you can see empirically there is something about the two-phase estimator that is relying a bit on your nuisance parameter assumptions, how you're modeling it. I want to be sensitive to time, so I'm going to just briefly mention that there were cases where, depending on if it was the oracle or the marginal, you would see slight difference in the methods. It was hard to summarize, other than we did see, even though the generalized raking wasn't targeting the marginal estimands, that it would often perform well. And this is just an example of the risk difference for the base case. I do want to skip over to mention just a brief summary of our Plasmode simulation, where we were using complex data, remember, to model the treatment generating for antidepressant or psychotherapy. Outcome model was self-harm. We looked at these complex random forest trees for all components of our models. And we had quite a bit of missing, 55% missingness in this disease severity. So realistic confounding distributions, things resampled from people, the sex, the age, levels of anxiety in the prior year, history of hospitalization. These were variables that were told to us from our topic matter experts. They were discretized with much more detail in the data generating. We applied simpler models with fewer interactions just to see, and I'm going to sort of this similar kind of picture with much more complex data where all the models are wrong. Thinking about a 5-year outcome, so more events, maybe 300 or so, and a 1-year outcome with fewer events. And the patterns were very similar from what we've seen before, other than to briefly mention some of the differences. So the similarities and the differences. The similarities, when we had the 5-year outcome, which had more events, then we saw that actually mice in generalized raking were performing similarly, and in the imputation model was actually doing slightly better, maybe 5% lower in terms of its root mean squared error. But both models kind of looking the same in terms of the coverage. But when we got to the more rare outcome, then we could see, which would be the lighter first 2 bars, that there were problems with the random forest having a little bit of bias, or its confidence intervals not working well, just like in the synthetic data. But what we found was, overall, even though everything was misspecified, a lot of the estimators were doing particularly well in getting close to the 95% coverage. And I think that's because in our data set, it was relatively weak confounding, weaker than what we had done maybe in some of the synthetic scenarios, definitely where we had very strong, maybe unrealistically strong patterns in the missing data. Although who's to say what's realistic is probably a bit of an overstatement there. So there were some nuances that the TMLE, I want to definitely highlight, that it did maintain the best coverage. All of the estimators had some problems with this misspecification that was, the data generating was more complex than any of the working models. The TMLE was unique and is the only one that could hit the oracle estimand, say, for the risk difference. And that's a really important result. But we can see there's this efficiency issue where it's got the widest confidence intervals. So we want to think about, if you're going to use this method, if you really care about valid confidence intervals, going to really want to think about robust sample sizes, I think, is one takeaway message. So let me wrap up. We're going to post this. There's a lot in the seminar, but we have a lot of code and vignettes to share. We'll be posting at this website in the coming weeks. Please contact me if you're looking for something and you don't see it. And our final conclusions are that these estimators, survey calibration, generalized raking, and I want to add here TMLE also, that's just a typo that I didn't put it in the top line, that they're rarely performed in biomedical settings and applied literature, but they really did perform, I think, consistently better overall in the setting of high missingness in the confounders. And each of them had some advantages that I think are worth considering. And that was, we were really excited to see those results. We did see imputation performing well in some settings where you could predict, either had a lot of data or you could have simpler outcome models. But one issue was, even like in our Plasmode, actually MI had really good efficiency, but it wasn't always the same algorithm. So I would need to have magic knowledge that in the marginal estimand, in this particular kind of data generating, I should have done mice, but in this other setting, I should have done random forest. So that was making us uncomfortable without knowing which one to do in advance. Even though the best efficiency was there with mice for one of the algorithms, it wasn't always the same one. So I do think we are willing to declare winners of survey calibration and TMLE. Our numerical, our work highlighted, it's really important to do numerical experiments as best as you can to emulate your data, because it isn't obvious that one method does well for all purposes. And so I think Plasmode simulation is a really useful tool. And one final caveat is our scenarios are comprehensive but not exhaustive. So it would be good to continue your own research for your own data sets. So thank you very much. Sorry that went a smidge long. Didn't leave too many time for questions, but I'm happy to have any that we have time for. Thank you very much.
That's great, Pam. Thank you. That's a tour de force and really nice job of leading and summarizing the presentation. So this floor is now open for questions. We have maybe time for a couple of questions. So feel free to type your questions in. As I said, your lines are muted. So as people are thinking of questions, I can probably ask you one question quickly.
For the conversation, or
So Pam, did you mind commenting on scenarios where you may have many confounding variables that are missing at the same time? So do you think, have you looked into scenarios like this? And what's your kind of gut feeling with respect to performance in those situations?
I think you cut out just a little bit. Would you mind just repeating that?
Oh, yeah, I was curious about situations where you have multiple confounding variables that have missingness at the same time. So I was wondering if you explicitly looked at the performance of these methods in those settings.
Yeah, so for our setting, we noticed, we didn't have a huge number of variables, but it was enough to cause trouble. And so we did look at where we had two variables prone to missingness, one that was strongly related to treatment and one that was weakly related to treatment. And so we did look at that that exact scenario.
Great. And there was one question that came in through chat, actually, was wondering, the person was wondering about the odds ratio and non-collapsibility of the odds ratio.
Yeah, no, that's a great question. So that's why, in part, we had to distinguish between this idea of the oracle estimand and the census estimand, or the estimand from our working model. If one of them had extra variables, then clearly those are different values because the odds ratio is not collapsible. So that's actually one of the driving factors for why we needed to define what was our benchmark. For missing data methods, a lot of the literature is satisfied with, well, let's just get the answer that we would have had we had complete data. But causal inference has raised the bar, right? They want the true treatment efficacy from the point of view of a marginal risk difference. And so then that's why we did, we had this oracle, which is meant to address, there is no such thing as collapsible anymore because we're going after the marginal risk difference.
Excellent. Great. So I don't see, we are at 2 o'clock. I don't see any other questions that have come in. With that, I would like to thank Pam once again for a great presentation. And for anybody who's interested in reviewing the slides or the presentation, once again, they both will be posted on our website, sentinelinitiative.org. So with this, we conclude the session and hope to see you next time.